Hi everyone, welcome or welcome back to my channel and welcome back to my series Learn with Me Data Science. So here is the sixth video of the series Naive-Bayes Classification. I am Vanshika Verma. In this video, we will cover Naive-Bayes Classification part. So let's move to the Naive-Bayes introduction. So naive Bayes is a probabilistic machine learning algorithm that uses Bayes theorem to classify data based on the probability of each feature given a class. It assumes independence between features, making it a simple and efficient classifier. Naive Bayes is commonly used for text classification, sentiments analysis, and spam detection. Let's move to the Python implementation of it. So in the first So in the first part of the code, we are importing libraries and loading the data. So firstly, we are importing the pandas library for data manipulation and analysis, and then we are importing the train test split function for splitting the data set into training and test set. And then we are importing the Gaussian naive Bayes classification from scikit-learn, and then we are importing the accuracy score and classification report function for evaluating the model's performance. Now we are now we are loading sample data sets. Here we are import the load erase function for loading the erase data, and then here we are loading the erase data set into the data variable. Now we are creating a data frame here. So df equal to pd dot data frame creates a panda data frame from the erase dataset feature data using the feature name as colon header, and df target adds the target variable class labels to the data frame as a new column named target. Now we are displaying the first now here we are displaying the printing the first few rows of the data frame of the to the console, allowing us to the preview data. So this appears to be the output of the print df.head function statement, which displays the first few row of the data frame. So sepal length, the mean displaying the length of the sepal in a centimeter, sample width, displaying the width of the sepal in the centimeter, and petal length, displaying the length of the petal in centimeter, and petal width, displaying the width of the petal in the centimeter, and target, uh, displaying the class label of target variable, which indicate the type of iris flower, which can be 0, 1 or 2. So this row represent the rows represent individual iris flower, which their corresponding measurement and class label. Like 0 flower has this sepal length, this sepal width, this petal width, and petal width, and the target of our 0 is this. So now moving to the next part of the code, which is splitting the data. So splitting the data, we are splitting the data into features and target. We can say it x and y. So x df dot drops the target column from the data frame, creating a new data frame x with only the feature column, which can be sepal length, sepal width, petal width, and y equal to df target selects only the target column from the original data frame, creating a new series y with the class label. And now we are splitting data into training set. So x train, x test, y train, y test equal to train test split. Splits the data into training and testing sets using the train test split function from skitlearns. Test size equal to 0.3 specified that 30% of the data should be used for testing, and the remaining 70% for training. And random stat 42 sets the random shift for reproducibility. Now we are printing the size of the training and testing set. Print training data site prints the shape of the training data, which can be number of rows, number and number of column, and print testing set can print the shape of the testing data, which can be number of rows and number of columns. So this code prepares the data for training a machine learning model, splitting it into features that can be X and target that can be say Y, and then into training and testing sets. Now moving to the third part, which is training the naive Bayes model. So the first we are training the model here. So first we look, before moving to training the naive Bayes model, we see the output of the splitting data, splitting the data code. So the code says training data size which with 0, 105 and 4, and testing data size is 45 and 4, which means the training data size is 105 and 4, which means there are 105 rows in the training data. Each row has 45 columns, which correspond to the sepal length, sepal width, and petal length, petal width. And the testing data set size is 45 and 4, which means there are 45 rows in the testing data. Each row also has 4 columns which correspond to the same feature in the training data. This suggests that the data was split into the training set with 105 sample and a testing set with 45 samples, with each sample having 4 features. The testing set is approximately 30% of the total data, which is consistent with the test size with 0 0.3 parameter used in the train test split function. So let's now move to the third part of the code, which is training the naive Bayes model. So here we are training the model. So in the first line, model equal to Gaussian NB, which creates an instance of the Gaussian naive Bayes classification, and model dot fit trains the model on the training data X train and XY train, and then predicting on the test size. Y predict uses the trained model to make the prediction on the test data with X test, and print predicted label prints the predicted label for the test data. This code trains a Gaussian naive Bayes classifier on the training data and then uses it to make predictions on the test data. The predicted labels are then printed to the console. Note that the Gaussian NP classifier assumes that the feature follow a Gaussian distribution, which may not always be the case. However, it is a simple and effective classifier that can work well for many datasets. Now move to the output. So the predicted labels are an array of value where each value correspond to the predicted class label for a sample in the test data. The values are 0, 1 and 2. 0 for Iris setosa, 1 for Iris versicolor, and 2 for Iris virginisa. So the predicted label suggests that the model is making prediction across all three classes, but with varying degree of the confidence. To evaluate the performance of the model, we would typically compare their predicted table to the actual label in the dataset. Next, we might want to calculate matrices such as accuracy, precision, recall, and F1 score to get a better understanding for the model performance. Now we are moving to the part evaluation model. So in the model evaluation code, we are printing uh, accuracy and calculate it also with which is a proportion of correctly classified sample, and then we are printing classification report, which provide a detailed summary of the model performance, including precision, recall, F1 score, and support. So precision is the proportion of true positive among all predicted positive sample, as we understand in our previous videos also. And recall is proportion of true positive among all actual positive sample. F1 score is harmonic mean of precision and recall, and support is the number of actual sample in each class. The classification report provide a more detailed evaluation of the model performance than accuracy alone, and can help identify areas where the model can be struggling. Let's see the actual output. So this is the output for this code. First, It gives the accuracy which we will print firstly. The accuracy which it is given is 0.9777, which is tends to be 97.78%. The model is correctly classifying approximately 97.78% of the sample. Now moving to the classification report, with precision recall F1 score in support. Precision is for class 0, precision is 1, which is perfect precision. Recall is also 1, which is perfect recall, and F1 is 1, which is perfect F1 score, and support is 19 sample. Now moving to the class 2, with precision 1, which is also again perfect precision. Recall is 0.92, which is 92% recall. F1 is 0.96, which is 96% F1 recall, and support is 13, which is 13 samples. Now moving to the class 3. Class 3 precision is 0.93, which is 90%, which means 93% precision. Recall is 1, which is perfect recall. F1 score is 96% and support is here also 30. Now macro average. So the macro average matrices are all around 0.98, indicating excellent performance across all classes. Now weighted average. So the weighted average matrices are also around 0.98, indicating the excellent performance when taking into account the class distribution. Overall, the model is performing extremely well with high accuracy and excellent precision recall and F1 score across all classes. Now moving to the next part of the code, which is the last part also, which is visualizing the results. So here we are visualizing the results in a confusion matrix form. So here we are firstly importing the necessary libraries. Here we are importing the C1 library for data visualization and matplotlib.py plot library for creating static, animated, and interactive visualization. And here we are importing the confusion matrix function from sklearns. So we are creating a confusion matrix. CM equal to confusion matrix by test by pred creates a confusion matrix using the actual label by test and a predicted label by pred. Now we are visualizing the confusion matrix using the C1 class. So SNS heat map SNS.heatmap creates a heat map of the confusion matrix using C1 and not equal to true, displays the numerical value in each cell. FMT equal to D format the numerical value as integer. And CMap blue uses a blue color scheme for the heat map, and S stick label and Y stick label sets the x-axis and y-axis stick labels to the target names. Now we are customizing the plot. Plt.title sets the title of the plot. Plt.x label and y label sets the x-axis and y-axis labels. And now we are finally displaying the plot by plt.show function. So this code creates a heat map of the function matrix which provide a visual representation of model performance. The heat map shows the number of true positive, false positive, true negative, and false negative, making it easier to understand the model strength and weakness. So now move to the output. Output is the confusion matrix. Confusion matrix is a table that summarizes the prediction against the actual outcomes. So the output or confusion matrix says that the true positive, the number on the diagonal represent the true positive where the predicted class matches the actual class. So it is Iris Satosa, for Iris Satosa is it is 19, for Iris versicolor it is 12, and for Iris virginica it is 13. And false positive, which is the number of the diagonal, represent the false positive where the predicted class does not match the actual class. So it is for Iris Satosa it is 0, for Iris versicolor it is 1, and for Iris virginica it is 0. So now move to the uh, conclusion, or we can say summary. The summary is the confusion matrix shows that the model has high accuracy for Iris Satosa, which is 19 by 19. Iris high accuracy for Iris Virginica is 13 by 13, and good accuracy of for Iris versicolor is 12 by 13 with a one false positive and false negative. Overall, the model is performing well with only one misclassification out of 45 samples. So the here is all the code for the naive classification. Now move to the conclusion. So for the conclusion, we can say it is a very powerful tool, and we have a practical implementation for it. And that's it for this video. Meet you in my next video, which is on the topic neural network. Till then, keep smiling, keep exploring. Bye bye.